All right, lecture 4B, generalized measurement models, modeling observed data. This is where we take what we talked about the last time and put it into practice with real data using factor analysis assumptions. Sound good? Hope so. Okay, so the objective of this lecture is to show different modeling specifications for different types of item response data and to show how parameterization might differ from standardized versus marker items, with things we just talked about in lecture 4A. We're going to again use the conspiracy theory data, 177, a sample of 177 undergraduates, answered 10 questions, all with 5-point Likert scales. You know the items. Here are the data themselves. All right, so first thing we have to do is we have to assume there's a latent variable that underlies a person's tendency to believe in conspiracy theories. This is the first step in that analysis that I was talking, or sort of the analysis steps we had before. This is step 0 that I didn't write down. Thinking of the theory, right? So mainly because I'm a psychometrician, that's my hammer, and all I see are psychometric nails, I'm going to assume there's a latent variable that underlies the chance that people believe in conspiracy theories. Do you ever believe that? If you're like, scrolling social media and you're like, there's a whole bunch of stuff about, I don't know if you're on whatever platform. Certainly the ones I look at, you get a bunch of people saying certain things like, the U.S. government can control the weather. That's one that I've enjoyed lately. I don't know about you. If you think of the people who post that stuff, I think it's a valid question whether it's a person's tendency to believe in that. And I'm guessing there are a few people who believe in it. It may be the case that someone else's, it may be related to some other type of latent variable like intent to manipulate information, intent to, confuse others. There may be other reasons why people share that. But let's go for today that there is this construct that a person might tend to believe in conspiracy theories more than others. And we want to go and try to measure where a person might be on that conspiracy theory scale. Mainly because then if we sell this to social media companies, they can target that person with some great posts. How's that sound? Okay, that sounds bad. But that's what's happened. Anyway. So for each person, as I mentioned before, we can denote a latent variable for each person as theta p. Right? Theta represents this unknown quantity. We're going to give it a number, numeric scale. We'll try to provide it to each person. And here P is the index for person, right? So I like to use subscripts that represent the name of the variable they're indexing over. So this is P for person. And we'll have 1 to capital P people. The other notation I have in my other convention I use in my notation is whenever an index is a lowercase letter, the total number of that index is the uppercase form, capital P in this case, right? So we have capital P people. And as I mentioned in the previous class, for the rest of our class, we're going to assume this latent variable is continuous, right? So it has a continuum from low to high on the real number line. And we're going to further assume that this latent variable is normally distributed. And for now, we know a normal distribution has to have a mean and has to have a variance or standard deviation. But we will go and put values into what the mean and standard deviation are as we go later. For now, we'll just generically leave those as placeholders. Mu is the mean of the latent variable, mu sub theta, and sigma sub theta is the standard deviation. Now, you're going to hear me when I talk about standard deviation. Let me just stop for a second and remind you 2 things. In most of my life, I've described the latent variable's variance and not standard deviation. So that's number 1. And number 2, Stan, when you use the normal distribution, does not want a variance. It wants a standard deviation as the second term. So for a univariate latent variable, I will often refer to this second term as a standard deviation. But remember, standard deviation is the square root of the variance. So if I slip and I describe it as a latent variable variance, please accept my apologies now. The rest of my life, I'm using variances. For this case, I use a standard deviation. Oh, and if you really want to go and do a facepalm, when you use a univariate normal distribution in Stan, you use the standard deviation as its second parameter, hyperparameter. When you use a multivariate normal distribution in Stan, it takes a covariance matrix as input, and the diagonal of that thing are variances. So Depending on how you specify your model, you may end up with a variance or a standard deviation. But we're going to start with the univariate. We'll call it standard deviation. Be aware that this is coming up. Okay? Okay. If now I'm gonna put a little math in these slides to sort of show what the likelihoods are. So I need to denote a set of things. So if you think I have capital P people and each one has a theta, I could take all of those and put them into a row vector here. So here, this capital theta, that's what this is, capital boldface theta, is every person's hypothetical latent variable that we didn't observe. Okay? All right. Well, let's build some measurement models. These were the steps I outlined last time. We need to specify the model, and then we need to specify how we identify its mean and variance, which I call scale identification. We have to estimate the model. That's fun. That's what we're going to talk about in just a moment. We got to examine model data fit or lack thereof, and then we need to keep going through those steps until we figure out if the model fits or not. There are other components as well. We'll get to those as we go on. So let's start with observed variables where we have normal distributions. Right, so you know in our example data, we have 10 items. Each item has a value of 1, 2, 3, 4, or 5 as a response. These are data that we would often use as an example for confirmatory factor analysis class. They're Likert type data, and there are millions of people throughout the world. I don't know if millions is the right number. How many people use factor analysis? I don't know. But there's lots of people out there who would say, yeah, just stick that in the factor analysis machine and get some results, right? So to do that, it makes a nice starting point. I don't believe, first of all, when we use a factor analysis, these are our data points right here. 1, 2, 3, 4, 5. There's 5 categories for each variable. Factor analysis assumes these things are fully continuous. Not only fully continuous, that they fall on the full number line. So not just between 1 and 5, but the whole line. That's really a difficult assumption to look at. But we use it because we like to think that, oh, we can approximate what people will say. It turns out these data factor analysis probably won't be a good approximation for, because each of these items is heavily skewed. Maybe not item 1 here, but many items have a big group of people saying, absolutely not, I disagree with this item 100%. And in such cases, the factor analysis assumptions assume these things look like normal distributions. And normal distributions are unimodal and symmetric, right? So we'd like to see a histogram almost like this first item, right? Where the most likely category is in the middle, selected is in the middle, and then the successive extreme categories have less and less people, almost like if you superimpose the bell curve over this distribution on its side, right? Not likely to happen here. But I'm starting there anyway, because in factor analysis world, we like to suspend belief anyway, right? We're sort of already playing with pretend variables. Yeah, it's a latent variable. Yeah, I forgot to collect it, or I couldn't measure it, that type of thing. So we're just going to add in the belief that they're all continuous and normal. What could go wrong? I don't know. But hold off on too much criticism yet, because we will get to the place when we get to the polytomous IRT model, we will treat this more appropriately as a categorical distribution. But we'll start with CFA because it's a little bit easier from a conceptual point of view, and the normal distribution is very well behaved. Okay? Okay. All right, so we're going to assume that there is a one single unidimensional latent variable model, and that latent variable represents the tendency for someone to believe in conspiracies. Right? So we would expect if someone's higher on this latent variable, they would have more of a chance of rating an item higher than otherwise, right? So if I'm a supercharged conspiracy theorist myself, I would be more likely to pick a 5. Unlike Vladimir, who doesn't believe in anything, he's a skeptic about everything. He's a scientist. So, sorry, Vladimir. You're going to say absolutely not, right? So that is the scale that we're looking at. And then we're going to assume that each response follows a normal distribution. This is the assumption we used in the linear models example in the first part of class, and it's the assumption you're using for your homework right now, right? And as I just laid out through several minutes of blabbering on, this assumptuation's tenuous at best. That's the academic way of putting it. If you want me to be frank, this assumption is BS, right? We think we can all say that. Why would you ever do that? Well, historically, CFA came first and it was the easiest to estimate. Factor analysis, actually exploratory factor analysis came first. So that's part of it, of how it happens. Kind of sus. That's a shout out to my son. There we go. Yeah, that's sus. Let me just give you digression because, yeah, who wants to talk Bayes? Let's talk son. He was like 7 or 6. He lost a tooth. Trying to be good parents, we do this tooth fairy thing, where we somehow take said tooth and return, and in its place leave some money. I don't remember how much the tooth fairy rate is these days, but inflation's hit the tooth fairy too, which is really like, I don't know, as a tradition here, or I don't know where. I only know because I grew up in the United States. I don't know where this tradition started, but how weird is that? Yeah, let me take that tooth that you no longer need and give you money for it. And then as a parent, you're like, what do I do with this freaking tooth now? Like, okay, throw it away. Oh, but they want to save the teeth. Ooh, that's creepy too. I don't know what the right answer is. Anyway, you know what I'm talking about? Anyway, he's like 6. This happens. He doesn't, he loses a tooth. We sneak some money into his room. Hey, he's found money. And then the next day he's like, I don't really know that there is a tooth fairy. Oh, really? Really? Why? Because you and mom, and he was telling me this, oh, well, you and mom are acting all sus about it. Like, okay. Good call, man. What do you think? Yeah, I don't think there's a tooth fairy. All right, tooth fairy won't show up anymore. The end. That type of thing. All right. Enough tooth fairy. Let's get back to the factor analysis. So we know the normal distribution before. This is the distribution. Remember, we talked in our last lecture about the distribution for the factors. Those are going to be normal, right? That's theta, but that's a prior distribution. We're going to talk about now is a normal distribution for all 10 of the items in our example. Every one of those will be normal. They don't have to be. We could actually mix and match distributions if we wanted to, but we're not going to. They're all going to be normal for this. So let's go back to that normal distribution. When we saw linear models, and in the homework that's due to tomorrow, you have an outcome variable y, and we assume it follows a conditional normal distribution, right? Which puts it on this regression style model for the outcome, right? So let's think about this. Regression looked like this. We said a regression equation was y is equal to some intercept plus some slope times a predictor variable plus error, right? And error follows some normal distribution with a mean of 0 and a standard deviation of e, sigma e sub e. We're pretty familiar with that. Last time, or in that homework and in that lecture 3 sequence, we showed that what really this implies is that the distribution of y should be normal. The mean of it should be the linear predictor part of the model, right, where we have beta 0 plus beta 1 times x. And the variant of the standard deviation of it should be the standard deviation of error. We saw all that before. This similar thing is going to happen for each item as we go forward here. All right, so for us, we can write out the CFA model for all 10 items, right? So now we have 10 variables, not 1, but 10. And each one is y. So every person's item response. So person 1 gave us 10 responses. We're going to call that y1 through p1 through p10. Every one of those will follow have a single predictor that's theta. So here, our latent variable is theta. We have to pretend that we observed it. So we basically say, hypothetical, if we had observed the latent variable, how would we build these 10 regression models to run all at once? So we specify it as if we had observed it. We have a linear predictor for each factor. We mentioned before, mu1 represents our item intercept. So this is the intercept for item 1. It's the value, the expected value of the outcome, or the expected rating value for a person whose theta was at 0. Right? Its latent variable is at 0. Lambda 1, we would call the factor loading in factor analysis. We never use the term discrimination in factor analysis, but we call it factor loading, sometimes call it slope. Lambda 1 represents the change in the expected score or the expected response level for a 1-unit change in theta. Now, what we would expect is if a person's theta represents their tendency to believe in conspiracy theories, then saying a person goes up 1 unit or 1 standard deviation on theta, we would expect this factor loading to be positive, indicating that as theta increases for a person, their numeric score to an item also increases, right? So if my theta is 2 and Vladimir's theta is -2, you would expect me to rate items on more like a 5 or a 4, where he might rate them as a 1 or a 2. And that's what the model is trying to build out. We also have error. Because we're in this linear model sense with a normal distribution, we often just put error on the line itself. You'll note when we get to IRT, error somehow disappears. It's still there, but it's just not noted. Error will follow a normal distribution. The mean of error is always 0. And the variance of error in this case has a special name. The parameter is called psi. And the variance is not called error variance or residual variance. It's called unique variance, right? This is how much variation on the item is left over after we explain variance based on this latent variable. Okay? So unique variance is directly related to residual variance, or residual standard deviation, in our sense from before, our linear model. But because we have 10 outcomes, where I have 10 dependent variables here, we'll have 10 unique variances. Similarly, we'll have an intercept for each item. We'll have a factor loading for each item. How's that sound? Excellent. All right, so our measurement model parameters, I just went to all of these. I just said that. You can see it. Come back to this slide if you need it. Anybody have any questions? No, I'll try not to be too repetitive. I'd like to be repetitive on the hard things and not on the easy things. How's that sound? All right, so we just specified our model. Boom, hooray. Next, we need a scale identification method. Right? Remember, scale identification, set the mean, set the variance. And because it's super easy, relatively speaking, we'll just assume the mean of the latent variable to be 0 and the standard deviation or variance to be 1. Right? They're both equal to 1, right? In that case, we have a standardized latent variable, meaning a person who is at 0 and a person who is at 1 is 1 standard deviation apart. So every unit difference is a standard deviation, equivalent to a standard deviation. And that makes we call it standardized variable because it's like a z-score, mean of 0, standard deviation of 1. All right, who's ready for the fun part now? Who wants to build this in Stan? I don't know. How many of you like it when, let's do a would you rather. My son's into would you rather. I speak 4th grader, sort of. What's this GAT thing? Anyway, never mind. Would you rather hear me talk about psychometrics or see me code about psychometrics? That's the two choices. I'm not going to let you choose, would you rather go take a nap or would you rather go get coffee? Because I would yes for both of those, right? Maybe not nap. Who knows? All right, let's do this in Stan. There are a few changes. So it turns out what I taught you about linear models will be very similar to what's in Stan. But there are a few changes that we're going to have to make, right? The first one is we don't have a model predictor matrix. Remember at the end of our linear model section, I said, oh, look, you can use the model.matrix function in R to create a matrix, a design matrix or a matrix of predictors, right? And then input that into Stan, and it would run for any set of predictors. Well, it turns out for us, we're not able to do that in factor analysis because turns out theta would be one of the columns of that matrix. And as you know, because we didn't observe theta, that means every step of the Markov chain, we're going to have a new estimate of theta. So what we would have to do, if we were to code Stan, we'd have to do that on our own. But there's no way to get Stan to input it that way. So we can't use the model matrix. The other bit that's a little bit different is that now, last time we had one outcome, right? One dependent variable. And I just, at the very end of that Stan code, we just had a section for y. So when we built our Stan data, there was one y that went into the list. Well, now we actually have 10 y's, right? We have 10 different variables. So instead of submitting it as one vector of like a floating point number, real number vector, we'll submit it as a matrix, right? So now there'll be 177 rows, or people are in the rows, and then 10 columns for items. Okay? And then finally, the parameters will be specified as vectors for each type. So at the end of our linear model example, I ended with a vector of beta coefficients, right? We had like 6 predictors, or between we had a continuous variable, we had a categorical variable, and we had their interaction, right? So we had beta in a vector. All right, so remember we had 1 outcome and 6 predictors. Now it's flipped. We have 10 outcomes, and for every outcome we have an intercept, and for every outcome we have a factor loading, right? So the item intercepts will all show up as a vector, and the item factor loadings will all show up as a vector as well too, right? So we're sort of switching things around a little bit, but that'll show up. Okay? Okay. So, I actually like to start with model, and I wish I would have done that first. Let's go in the model block first. Okay? Okay. I flipped ahead to slide 18. How do we do this in the model? Well, it turns out, remember, we have 10 items. Each item I'm going to note as Y. And remember, we're putting this in a matrix, right? So the columns, each column of this matrix represents one vector of observations. So I make a loop right here where we're looping across each of the items, right? And the word item is my index for the loop. By the way, my coding convention is I name the index variable. I don't like I, J, and K. Right? That doesn't tell me what it does. I'm looping over each item, so I have item here. So for a given item, the model on the mean side is item intercept, which is mu for that item, plus item factor loading, lambda, times theta, which is our latent variable. So here, what you'll note is mu has item in brackets, and lambda has item in brackets. And that's because mu is stored in a vector, and theta is stored in a vector. So I have to tell it which element of that vector is used for each item. Finally, the residual, or the unique standard deviation, remember this is not variance in Stan, also has a bracket. That's the psi term, and that is what we estimate with each. All right, so now this model, here is the linear predictor. Mu plus lambda times theta shows up in the mean side, and psi is our unique variance, unique standard deviation as we go forward. Questions on any of this so far? Pretty straightforward? So? Let's see. Okay, let's go and put priors on these things. Theta. Theta is actually a vector as well too, but every theta in that vector we can shorthand and say that theta follows a normal distribution with a mean of 0, standard deviation of 1. Right? That is fairly straightforward notation. That's why I like starting with a standardized factor to begin with. Right? So theta has a prior distribution that's with hyperparameters 0 and 1, mean of 0, standard deviation 1. Each of our item parameters, lambda, mu, and psi, I'm going to say follows a multivariate normal distribution. Right? I could have just done the same thing as theta here, but multivariate normal allows me to have a different mean for each and a different variance or potentially covariance for each. This was what I had done at the very end of the linear model section. I defined a beta vector, and I said it followed a multivariate normal. In our case, what we have to do is just tell it the hyperparameters in a vector for the mean, and down the diagonal, the variances as we go forward. There's a reason for this that I'll get into as we get a little bit further into the estimation here. Mu follows a similar multivariate normal, and you'll note the hyperparameters for mu, mean mu, and covariance mu are the same structure as lambda, but they're different names, and that's because we may have different values of the hyperparameters for either of these parameters. Mu and lambda tend to be on different scales, right? I can tell you in a factor analysis model, mu should approximate the item's actual mean, the mean of the item, when we have a standardized latent variable. So Mu we would expect to be somewhere between 1 and 5, just based on the premise of it. Lambda, on the other hand, may have a different mean altogether. In fact, it's usually in a standardized factor somewhere that's between 0 and 1, maybe a little bit larger. So any questions on mu or lambda so far? No questions. Moving on then. Now remember, psi is our term for the unique standard deviation, right? The square root of the unique variance for each item. It's a vector, but I can apply the same rate parameter for each. This is me getting lazy. I'll just have one rate parameter for each item to make it a little bit easier. And let me just double check I did that. Nope, actually that's not true. If psi is a vector, we can actually give it a vector for parameters as well. So this psi rate has a different rate parameter, and I'm using the exponential distribution. If we recall from the linear model slides, we used exponential for the residual variance. And we played around with the value, like an exponential with a hyperparameter of 10, kind of had this sharp slope around 0, where as the hyperparameter got lower and lower, the PDF got flatter and flatter. So exponential gives us the ability to do that. So that's our model. All right, so now what I like to do in Stan, I talk the model first. Let's go backwards. Let's talk parameters, right? We can even see the parameters here. Theta is a parameter, psi is a parameter, lambda and mu are all the parameters of the model itself. So when we go back to the parameter block, you'll see that. We have theta listed here. We use the term vector, and we tell it the size. Number of observations is the size. In our case, 177. So that vector for theta indicates that theta is a floating point number, right? A floating point number meaning it has values, decimal values, right? It goes on the real number line between negative infinity and positive infinity. So when you see the word vector, you realize that that's a floating point number. So mu is also a floating point number. It can take any value. And again, it has the number of items is the number of mu's that we have. Lambda is also a vector. Psi is also a vector, but psi is unique in that it has a lower bound because variances cannot go below 0. So this ensures that Stan doesn't initialize the variance to be a weird number. With using an exponential prior, that should keep things positive, but when Stan starts estimation, it may start to have a problem here. Okay. How are we doing? Okay. There's a foreshadow part down here I'll get to in just a minute. Let me go back and talk data now. So we know what we need to import into Stan now, right? From our model block, we saw we needed y, and y should be a matrix. Each matrix has a set of rows, 2 dimensions, rows and columns. Here, number of observations is rows, columns is number of items. So if you think of it, we have 177 observations and 10 items. This should be a 177 by 10 size matrix. That's the same thing that you would import into Lavon or M+. It's the same structure. We could have changed the structure if we wanted to, but it's fairly straightforward and fairly simple to do. Of course, I just blanked on my connection. Let's see if this works. Actually, if you don't forget the connection, I've got these slides right over here. This feels like a cooking show now. Like, oh, and now I just made these slides. These slides take like 10 minutes to build if you try to build them on yourself. It's a lot of Stan going on here. All right. So here, y is, we talked about our matrix. We need to tell it how many items we have, right? Because that's a variable. And we need to tell it how many observations we have. That's a variable. And I just put the lower command in just to make sure that we didn't somehow submit a negative number to build that. Now we also had the matrices or the vectors of hyperparameters as well. So what we need to import into Stan for mu is a mean vector, right? Just a set of number of items. It'll turn out to be its mean. We'll also import a covariance matrix. Now that's a matrix that's size 10 by 10, items by items. The diagonal of that matrix has our hyperparameter for the variance of mu, right? So because mu, we're saying, follows a prior distribution that's normal. The variance will show up here in the diagonal of the covariance matrix. All of that I just said about mu is the same for lambda, but we need to potentially have different values for the hyperparameters, so we allow a different set of mean vector and covariance matrix. And then finally for psi, its rate parameter will have a vector for one hyperparameter for each item. So that allows us the possibility of selecting different priors for different hyperparameters for different items. If you wanted to do that, that's perfectly acceptable as we go forward. Any questions on any of this? Okay. I want to show you one thing, though. Here's an issue. Our parameterization of lambda right here can be a bit of a problem. So what Stan tries to do when it seeks the posterior distribution is it uses this Hamiltonian process, Hamiltonian dynamics. And it has this momentum parameter that you don't know what's happening. It's behind the scenes to help suggest where a proposed value. Remember, in a Markov chain, we propose new values. This is rejection sampling. We're proposing new values for every parameter for every iteration. And Stan uses this sort of process, a physical process almost, that tries to seek values that are up a slope of the posterior distribution, right? The problem with us, though, is as we start out, lambda times theta has another value that may be equally likely. And that is, turns out lambda theta is equal to negative lambda times negative theta, right? So what that means is, if we're not careful, we may end up with some chains that converge to a positive lambda and some chains that converge to a negative lambda. So within chain, it looks super converged, but between chain, we may have different values, and those values are reflected across zero, meaning we have positive lambda here and negative lambda down here. So that's one thing that we're going to see pretty quickly. And here I'm showing you that with some starting values as I go forward. You're going to see this coming up. So that whole process right here is in part due to Stan initializing all of our lambdas and all of our thetas right around 0. Right? They're between they're initialized between -2 and 2. Because each of these values does not have a constraint on it, that it is equally likely, if you're right about 0, it's equally likely to move toward the mean that's on the mode that's on the positive side versus the mode that's on the negative side. So we have to worry about that going forward. Okay, so let's talk about prior distributions a bit. Actually, any questions on anything I just shared? No questions. Let's talk about priors then. There's not uniform agreement about which priors to use. We're going to use uninformative priors as much as possible. That's sort of my Bayesian philosophy, particularly in psychometrics. I like to use uninformative as much as I can, mainly because I'd like the result to look more like the data and less like what I think the data should be. For now, that means for the item intercepts, we'll use a normal distribution. Actually, you saw it coded as normal distribution. And the variance for each hyperparameter will be 1,000, right? We'll center it at 0, but the variance of 1,000. Now, we know, again, we have to talk about what we expect these parameters to be to do priors. So in the linear model, in this case right here, where we have the mean of theta being 0, you can show that this model should approximate, mu itself should be the mean of y. You can take the expected value of this equation and show that, right? And since we know that each one of our y's is a number between 1 and 5, we know the mean for each item has to be between 1 and 5. So you may think to yourself, Jonathan, why are you putting a 0 here when I know the mean can't be 0 and it has to be between 1 and 5? And my reason for that is because my variance is so large that the range of 1 to 5 is virtually equally likely under this normal distribution that I've specified here. So I'm not putting a lot of information on this with a large variance. Does that make sense to you? All right. Now for the factor loadings, I'm also going to give a normal distribution here. Mean of 0, variance of 1,000. And you might question this because, as I mentioned before, we might have this bimodality right here because the modes are the same. But let's hold off on that for a moment. There are a number of Bayesian psychometricians for measurement models that will constrain lambda to be positive. I don't like that very much because Well, let me back up. For unidimensional models, that usually works out. Unless you've miscoded like a reverse coded item, most of the time you will find positive factor loadings in unidimensional models. No problem. When you get to more complex models, particularly where there's more than one factor loading needed per item, like a bifactor model though, that may not work. So I tend to try to find methods that allow lambda to be any number. That gets me into trouble sometimes. It also puts me at odds to a lot of books that are written on the topic. But I firmly believe in what I'm doing, so I'm going to continue it. All right. Finally. Oh, the other thing I will mention about lambda. It's a unique parameter in that the higher lambda happens to be, the more an item relates to the factor. Right? The more an item relates to the factor, the more informative that item happens to be as well, usually, too. Right? In CFA, it's actually the ratio of lambda to psi squared tells you how much information. But what I'm saying about that is, if I force lambdas to shrink towards 0, now this is an uninformative prior. So the range of lambdas I'm expecting are somewhere between 0 and 2. A normal distribution with a mean of 0, variance of 1,000 is likely to be roughly equivalent between those two values. Not a lot of difference. But if I need to make this more informative, maybe because of convergence issues, maybe because I have a stronger belief, I like to make the informative prior force lambdas closer to 0, because to me, I'm not cheating psychometrically then. Right? If I make a informative prior on lambda and I make the mean 2, when really the means are probably, the posterior modes should be somewhere around 1, what have I just done? I've made it so that I think I know a lot more about where a person's theta happens to be than I really actually do based on my data. So my choice of prior for loadings, factor loadings, is almost always very conservative in that I force them to be 0. Because to me, that just means I will claim that I know less about where a person is on the scale. And finally, we'll use exponential 0.01. We saw that before. Oh yeah, this is the range. All right, so normal distribution, if we look at between 0 and 5, these are like we have to get out to the third decimal place to see. I guess it's the fourth decimal place to see differences. That's fairly uninformative. The curve looks really steep, but look at the scale, right? Similarly with exponential, between 0 and 2, which is where I would expect these unique variances to be, or unique standard deviations to be, it also is very, very small differences. That looks like a really sharp curve, but look at the numbers of the y-axis, right? You have to get out to the third decimal place to see it. So this is actually uninformative for the prior, is what I'm arguing. Okay, this is our list in R. I just want to skip ahead. We have 1 minute left. I want to show this result. That is what I got. Actually, let me leave it here. I got intercepts that work, but take a look at these point estimates, these R hat values. Right, this is my model result. So that tells me I'm converging on intercepts. I'm converging on unique or residual variances, standard deviations. I am not converging on my factor loadings. I see a look of like Linguo, you look like you're just really disappointed in this analysis, and I like that look, so that's good. That's how I feel too. I want to leave you with this and let you think about that over the weekend. We're out of time for today. But this is the problem I was talking about. We have to be a little bit hard. It's a little bit harder to specify a latent variable model because remember, lambda multiplies the thing that doesn't exist. And so we're trying to simultaneously estimate the thing that doesn't exist and then put it in a regression model with a slope that does. That's difficult. So I'll leave it for that. Does anybody have any questions before I stop today? All right. Have a great rest of your week. It's great to see you. Thank you for being here, and I will be back next week with more of this to talk about why that is. Take care, everybody.